All right, everybody, I've got 12 noon on my clock, so let's go ahead and get started. Welcome to our first semester study guide review. We're going to be spending about an hour today just going over the study guide, going over what we have or maybe have not gone over in class, and giving you all an opportunity to actually go ahead and ask any questions that you have related to the study guide. As a reminder to the students, you guys have basically a lot of the questions from the exam in your hands, just with slightly different numbers. Um, as a reminder, if you do not have the study guide in front of you, the paper copy you should have gotten in class, go ahead and jump on a Schoology. I did put a digital copy of the study guide there as well. Now, as far as the study guide goes, we are going to skip over part one in its entirety. The reason being is that you guys have that, and I'm going to show that to you here right now because we actually have all those definitions in Schoology. So on our class pages in Schoology, and let me flip this over to our to the display so you guys can see what's going on. So on our class pages in Schoology, I've just got 1A pulled up here, but what you'll see is that you've got this final exam black folder right here, okay? If you open this up, this has a link to today's video. It has the study guide, but then it has these three definitions pictures here. These are literally pictures of the whiteboards and the Promethean from class. So you guys can copy the definitions from there so that you have all those definitions from page one. Today, what I want to be focusing on is actually the practice problems rather than the definitions and everything, okay? So that being said, I had a couple of students ask some questions in class as well. And so what I'm going to do is I'm going to start with those class questions because I don't see anything in the chat. Once I see something in the chat, though, for sure, I'll be happy to answer your guys' questions. But for right now, I'm going to go ahead and address some of the things that came up in class. So let's go ahead and get started on that front. The first question that I had in this regard was on the first page, and this is identifying the factors of a graph polynomial. So let's go ahead and flip over to our display. So you'll notice I've got my Word document with my stuff directly in front of you. So I've got my Wacom out so I can go ahead and write everything down on here. So when you're identifying the factors of a graphed polynomial, right? And this goes back to our first unit. This is stuff we were covering in August and September, okay? So not remembering this stuff, totally okay. All right. But the first thing we need to do is we need to identify our zeros. And in particular, we have 3 zeros in this particular graph, okay? So remember that a zero is where the graph crosses the x-axis, okay? Where the graph crosses the x-axis. Okay, now when we're talking about where the graph crosses the x-axis, the important part that I want to bring up here is that each of these is at a specific point on the graph. Now I'm going to zoom this in a little bit so we can see that there are numbers here, right? You've got 4 here, 2 here, -2, -4. And in particular, this point right here where the graph is crossing is at -3, okay? So what this says is -3 is a 0, or when x equals -3, y equals 0. Looks like that as a Cartesian coordinate, okay? Now, what this boils down to for us is that this value right here has a corresponding factor that will result in this being 0. And this is the way this works. If x equals a, then x minus a is the corresponding factor. So in this case, if x equals -3, then x minus -3 is the corresponding factor. Remember, when you subtract a negative number, it is the same thing as adding, okay? So that way you get x plus 3, and that makes sense, because if you plug -3 in for x, -3 plus 3 equals 0, right? It results in that factor zeroing out. So what about these other two factors here? Well, here we have a +1. So if x equals 1 is a 0, then x minus 1 is its corresponding factor. And then over here, we have x equals 5, right? Because you notice 2, 4, over here is 6, so halfway between 4 and 6 is 5, okay? So therefore, x minus 5 is the corresponding factor, okay? So you have 3 zeros, and you have its corresponding factors. That's it. You're done. You have successfully identified the factors of that polynomial, okay? Now, down below, there's another example that I would like to show you, and that's this one right here. This identify the factors of each of the graphed polynomial and the multiplicity of each factor. Okay? And the way I have this sentence structure set up is that it says the multiplicity of the factor blank. So we're going to fill in what the factor is here. And then after filling in what the factor is, we're going to identify its multiplicity. Now, multiplicity, term we've gone over before, but we're going to go over it again after we identify these factors, okay? So our first factor right here, right? We have 0, -2. Notice that these thicker lines here are every 2 units, which means that this is going to be -3. So this 0 right here sits at -3. So if x equals -3 is a 0, we just talked about this, right? X minus -3 is going to be its factor. And that's exactly what we would write right here is x plus 3. Okay? Then our second 0 is right here. Okay, but you'll notice we only have 2 zeros in this one, so we're only going to have 2 factors. Right? Now this 0 exists at x equals 1, and you'll notice that these are both factors that were present in the previous problem. So x minus 1 is the corresponding factor. Now here's where multiplicity comes into play. Okay? Multiplicity tells us how many times a particular factor would appear in the factor form of that polynomial. So if we were to write out the full factor form of this polynomial, it would contain these 2 factors, but there would be a different number of iterations of those 2 factors. Okay? And that is determined based on how the graph interacts with the zeros. So for instance, over here at x plus 3, where it's just passing through, if you see the graph pass through like that, that means you have a multiplicity of 1. Okay? That factor will only appear once in the full factor form. So if we're writing the full factor form, we can just say x plus 3 like that. Now, the second one is if it bounces off. Okay? If it bounces off, such as what's happening at x equals 1 here. Okay? Notice that at x equals 1, right, the graph comes down, it touches that 0, and then bounces straight back up, okay? If it bounces off, you have a multiplicity of 2. And what that means is that the corresponding factor here, if you were to write the full factor form out, would actually appear twice rather than just once. And the third example, which we don't have here, is a curve through, and it looks something like this. Okay? If you see something like that, that is called a curve through, and that has a multiplicity of 3. I will tell you this is not on the test, but you definitely want to know it, okay? Because while it's not on this test, it may show up on your ACT, EOC, something like that, okay? But then you finish these sentences off. The multiplicity of the factor x plus 3 is 1. And the multiplicity of the factor x minus 1 is 2. Boom. That's it. You're done. Nice and easy. Nothing too complicated there. You've got yourself a quick, simple solution to a quick, simple problem. If I remember correctly, I formatted this one to where it is a drag and drop response on the final. So keep that in mind, that you're going to have a nice little drag and drop response section that you can work with, okay? Now, I'm going to click over here to the side. Try. Nope, that's not what I wanted to do. There we go. Okay. The other one that I had a question on was this right here in the middle. The polynomial p is a function of x. Now the graph of P has 4 zeros at -4, -2/3, 0, and 9. And all we want to do here is write an expression that could represent P. Now we have the zeros. And if we have the zeros, then we can get the factors. Okay? If we have the zeros, we can get the factors, meaning it would be very easy for us to write this function out in factor form. And as a reminder, factor form, you're expressing the polynomial as a product of multiple factors. Okay? So let's go ahead and establish these factors. We have a 0 at -4. Okay? What that means is that you have a factor of x plus 4, just like so. With a 0 at -2/3, you can have a factor at x plus 2/3, just like that. The weird one here is this 0 right here, because remember, if you've got a 0 at a point, then x minus that value is a factor, but x minus 0 is just x. Personally, if it's me, I put that up here at the front of the equation. Okay? And then finally, your last 0 is 9. So you can say x minus 9, and ta-da! Just like that, you've got the factor form of this polynomial. Now, right above this, I tell you to multiply the polynomial and write an equivalent expression to 2 times 3x plus 4 times x minus 1 times x minus 3. Now, this entire function up here is very specifically in factor form already. So we're multiplying it together and trying to put it into standard form. Okay? Multiplying them together to try and put it into standard form. So what we're going to do is we're going to multiply two of these polynomials first. Then I'm going to pick x minus 1 and x minus 3 because multiplying them together seems easier than trying to multiply any of them times 3x plus 4. Okay? So x minus 1 times x minus 3. Well, we got a FOIL. X times x gives us x squared. X times -3 gives us minus 3x. -1 times x gives us minus 1x. And then -1 times -3 gives us plus 3. All said and done, we combine our like terms here, and we end up with x squared minus 4x plus 3. And then we're going to take that, and we are going to multiply it times 3x plus 4. Now, once again, the way I like to do this, I like to track based upon what the values are. I'm going to change my color to red so we can see this a little easier, okay? So we're going to multiply this 3x right here times each of the terms. So 3x times x squared is going to give us 3x to the third, okay? Remember that we add those exponents together as we do this. 3x times -4 minus 12x squared. Remember, multiply the coefficients, but add the exponents. 3x times 3 gives us plus 9x. Okay? Brilliant, we've got that. Now I'm going to go ahead and flip over to blue so we can do the other side of this problem, because the other side of this problem is taking this plus 4 and distributing it to the other terms. So plus 4 times x squared gives us plus 4x squared. And look at where I put this, okay? So what I have effectively done by putting this here is I have created columns. And these columns are going to make it a lot easier to combine my like terms when I'm done. Positive 4 times -4x gives us minus 8x. And positive 4 times positive 3 gives us plus 12. Now, we go ahead and add all of these together. 3x to the third doesn't have anything else to add to it, so it stays by itself. -12x squared plus 4x squared. Here we're adding these two together, which gives us 8. okay, because we have a negative 12 and a positive 4, so it stays as negative 8x squared. Positive 9x minus 8x is plus x, and this plus 12 over here stays all by itself. It doesn't have anything else to add to it. There is one last step, though, that we need to remember to do, and that is this 2 right here. Okay, we need to take that 2 and multiply it times this entire thing. Fortunately, that's a lot easier than it might look, because what's going to happen here? You take this 2, multiply it by 3. That gives us 6, and x to the third stays the same because this 2 doesn't have any kind of variable attached to it. Okay? So 2 times negative 8 is minus 16x squared. 2 times x is plus 2x. And 2 times positive 12 is plus 24. This is your final full polynomial. Okay? So, those are the 3 main ones that I've seen questions about in class. I'm going to keep going through some of the other ones because nobody's dropped any questions in the chat. To those of you who are here, though, feel free to do so. Drop yourself a question in the chat if you've got anything that you want me to go over throughout this entire process. I'm more than happy to do so, but otherwise I'm just going to keep on keeping on here. All right. Another one I saw a lot of questions about during our review in class, because and any parents who are here, we did already do an in-class review. We actually did a day and a half worth of basically full in-class review, where I gave them the study guide packet, and they've kind of already done it a little bit. If your student is in my class on an A day, they're going to have a little bit more time, because we're going to have a full day of classes on Monday. So just as a heads up there. Now, let's go ahead and write out this equivalent expression. So we've got this problem right here. Write an equivalent expression to 2x to the third plus 11x squared minus 21x, all divided by x squared plus 3x. Now, when I'm looking at this, what I see here, the first thing that catches my eye is that every single term has an x on it. And since every single term has an x on it, I can factor 1x out of everything. Okay, so what that looks like is now I reduce all these exponents by 1. So that becomes 2x squared instead of 2x to the third plus 11x minus 21, all divided by x plus 3. Okay, so that's it. We factor an x out of every single term on this function. Okay, now that we have done that, this is just a basic polynomial division problem. Okay, so what we're going to do is we're going to set up polynomial division. We're going to say 2x squared plus 11x minus 21, and all of this is going to be divided by x plus 3. Now, when we're doing polynomial division, what we're trying to do is we're identifying, okay, I see this first 2x squared right here, and I'm going to do my best to eliminate that using x here as a factor. So we come over here and we say, okay, 2x squared divided by x. Now, I'm going to put in some of the understood math that's happening in the background, because there's some stuff you don't see that's still happening. And that is that you have a 1, an understood 1 right here. You also have an understood 1 right here. That is important because now what you can do is you divide these over here. So 2 divided by 1 still gives you 2. X stays the same, but what happens is we're going to subtract these exponents now since we're dividing, okay? 2 minus 1 gives us 1. And then what we can do is we can get rid of anything that could be understood. So this 1 right here can go away, and we simply have 2x that we're left with. Now, in order to subtract this, we take this 2x and we multiply it by both of these terms over here. 2x times x gives us 2x squared, which is exactly what we wanted. We wanted those to be equal. 2x times 3 gives us 6x. And just like when we're doing long division with full whole numbers, we're going to subtract these. 2x squared minus 2x squared, that cancels out, it's gone. 11x minus 6x leaves us with 5x, and then we carry the negative 21 down. That is step 1. Next up, we're going to take blue, and now we're going to try to eliminate this 5x right here, and we're still using this x over here. So we follow the same process. 5x divided by x. And once again, let's write in our understood numbers here. Because what happens is 5 divided by 1 gives us 5. The x carries down, and 1 minus 1 gives us 0. Now, anything to the 0 power equals 1. So this is effectively 5 times 1, which is just 5. So we have 2x plus 5. Same as before, we're going to multiply that 5 by both of these terms over here. 5 times x gives us 5x, and 5 times 3 gives us 15. And just as before, we're going to subtract both of these terms from our previous value. 5x minus 5x zeroes out. We don't have to worry about anything there. Negative 21 minus 15 gives us negative 36. Okay? Now, this negative 36 is a remainder, right? We can't divide anymore because we can't divide 36 by a variable like that. Okay? Well, here's what's going to happen with that. Okay? And we're going to format our final answer in green. So that 2x plus 5 does just like that. Then we are going to subtract 36 over x plus 3. So notice that we left our remainder above our fraction. Okay, we left our remainder in the numerator of our fraction. That is it. That's how we go about solving that problem, and that's going to be your final response there. Okay? Now, let's scroll on down. Another one I had a lot of questions come up on in class was this one right here on the second one right here. What is the solution to the equation 4 minus the square root of 4 minus x plus 7 equals 2? Now, this question is a lot easier than it looks. And here's why. It's because you can actually stop after one step. Normally speaking, what you would do is you'd say, okay, so we have to subtract 5 from, or subtract 7 from both sides of this equation because we have to get this exponent by itself. But because the exponent is tied up in the square root, we have to resolve everything outside of that square root before we can do anything with that. So we subtract 7 from both sides of the equation. That cancels this out here, leaves us with the square root of 4 minus x equals negative 5. And we are done right there. Now, some of you may be asking, okay, why are we done there? We still have a problem to solve. Except for this symbol right here. So this symbol is known as a radical, okay? And when you see it with no value here on the left, what that means is it's telling you to take the square root. But that radical symbol specifically refers to the positive square root. That square root is only ever positive. So if you set this radical equal to a negative number, it can't fulfill that equation because this symbol is always positive. What that means is that here you're going to have no solution. That's it. You're done. No solution. Okay? All right, logarithmic form. Okay? We've been talking logarithms and everything for a while now, but what we're going to do is we're going to convert this 3 to the x power equals 400 into logarithmic form. Now remember that logarithmic form is just the logarithm, right? It tells us 3 to what power would equal 400. Okay? So what we're going to do is we're going to turn this around. So we're going to start by writing log. That identifies everything else we're doing as a logarithm. Then we identify our base. Now our base is the same thing as the base of our exponent here. So the log base 3. That's taken care of. Now, this 400 right here is going to come over to the left-hand side. The reason being, the entire purpose of a logarithm is to solve for this x. So we need to have it by itself. So the log base 3 of 400 equals x. And that's it. You're done. You've written it in logarithmic form. That is literally how simple that problem is. Now, the next problem is not quite as simple. The population of a country in Europe was 5 million in 2015. Since then, the country has grown at a continuous rate of 3.6% per year. Write an expression modeling the growth of this country's population, and then identify what year the population will reach 7 million. So my advice to you on a question like this is to break it down, because it is two separate questions, okay? We're going to identify what those two separate questions are. So look at this. Write an expression modeling the growth of this country's population. Okay? This word right here, then, tells you you are completing a second separate task once you have completed the first task. Okay? Identify what year the population will reach 7 million. So your key first step here, you have to do what is in red before you can do what is in blue. Let me say that again. You must do what is in red before you can do what is in blue. That's what that then tells you, is if you don't set up this equation or this expression, you're not going to be able to do this blue. You have to set up the equation first. So let's use red and let's follow that instruction. Write an expression modeling the country's population. Okay, cool. So it starts at 5 million. 5 million, that's our start point. Okay? Now, our growth rate is 3.6%, or 0.036. We're going to convert this into a decimal right off the bat. Now, we have all the information that we need in order to set up this equation, but there's one key piece of information that I want to point out, and that is this word right here, continuous. Okay? That word continuous tells us that we need to be using a different format of a standard equation. So remember that there are two formats for an exponential equation. Okay, I'm going to kind of put this over here in a box. Okay, two exponential formats. Okay, format number one, we're going to call incremental growth. Okay, what incremental growth tells you is that let's take this population as our example, right? An incremental population would tell you, okay, every year on December 31st of whatever year it is, the population grows by 3.6% without fail. It means that everybody who's going to die for the entire year dies at the exact same time. Everybody who's going to be born for the entire year is born at the exact same time. All of those things happen simultaneously, and our population grows by 3.6%. Except that that's not realistic. That doesn't happen. What does happen is people continuously being born, dying, and that growth rate being in a smooth curve over time. Okay? So when we talk about this incremental growth, that's the standard non-continuous model, which we will use down here. Okay? Which says you're going to take your constant or your starting value, you're going to multiply it times 1 plus your growth rate, and then raise it to the power of t or x or whatever your variable is, right? Meanwhile, for a continuous growth rate, like our example here, okay, what's going to happen here is it's going to be your constant. You still start with the same thing, your constant, but this time it's going to be multiplied by the mathematical constant of E. Now, what is the mathematical constant of E? It's about 2.718, and it represents continuous growth. Okay, I'm not going to fully derive that number here. We have that video on the YouTube channel already, but the main point that I want to get across with this constant is that you're continuing to grow. All right, you're absolutely continuing to grow through this entire process. And we're going to raise this to the power of our growth rate expressed as a decimal times t, or whatever letter we're using for our variable. Okay? So now we have what we need. Okay, we have our constant or starting point, we have our rate, and we know what a continuous growth model is going to look like. So let's write an expression modeling the growth of this country's population, and that is 5 million times e to the 0.036 t power. That's it. You're done. That's what you had to do in blue. Or in red, sorry. That's what you had to do in red. Now, the blue side of this, identify what year the population will reach 7 million. That we have to go a couple steps further, because now what we're going to do is we're going to say, okay, I know the value. I know the population that I want to reach. How long is it going to take to get there? So what we're going to do is we're going to set this entire equation equal to 7. And that gives us all the tools we need to solve it, because now we only have one unknown. We have one variable. And since we only have one variable, we can do as we please with that one variable. So what we're going to do is we're going to divide both sides of this equation by 5. The reason being, this variable is in an exponent. Therefore, we can't touch the variable yet. We can't get it by itself, which means we can't touch t, we can't touch 0.36, and since it's associated with the variable very directly, we cannot touch e either. The only number we can do anything with on this right side of this equation is 5. So we divide both sides by 5, it cancels that out on the right and leaves you with 7 over 5 on the left. Or, I'm going to convert this to a decimal because I like decimals. 1.4 equals e to the 0.036 t power. Now, cool, we did that. What's our next step? Well, we can't go any further with the formula, with this equation, the way it's currently formatted. Okay? And so what we are going to do is we're going to convert this into a logarithm, exactly like we did up here. So we're going to say, okay, the log. What is the base of our exponent? That's e. The log base e of 1.4 is equal to 0.036 t. Now that t is out of the exponent, we can manipulate it more. And what we're going to do is we're going to divide both sides of this by 0.036. What that does, it cancels this out and leaves t by itself on the one side of the equation. Then t is going to be equal to the log base e of 1.4 divided by 0.036. Okay? And what I'm going to do now is I'm actually going to grab my calculator, and we're going to use the calculator in order to finish this off. Okay? So I've got it in scientific calculator version right now. You'll notice that I don't have a log base e anywhere on here. Actually, I do. The log base e is known as the natural logarithm, and its button is ln. So if I push ln right here, notice it gives me an invalid input. That's because the Windows calculator, when you use it, looks for you to plug in a value. So I'm going to plug in my 1.4, and then hit ln. Now it gives me that log. Then I'm going to divide this by 0.036. And doing that gives me the value 9.34. Now, I don't care about the decimals here. All right, I'm going to write this down. I have 9.34, but I really don't care about this 0.34 because the question asks me what year. Doesn't ask me what month, doesn't ask me what day. It says what year does all of this happen. So that means that the year is 9 years after our start. Well, what was our start? 2015. So we say, okay, 2015 plus 9 years later gives us 2024. So in the year 2024, that is when we are going to have this come up. That's when we're going to see, all right, this is when the year the population will hit 7 million people in this undisclosed country in Europe that I just made up for the purpose of this problem. Okay? That's it. Done. Bene, finito. Random Italian. Why not? Okay? Versus, down here below, we have in a non-continuous model, if you are given a starting value of 500 and a growth rate of 25%, what would the function look like? Well, notice, right? We just told ourselves up here. Here's our incremental function right here. That's a non-continuous model. So if we have a starting value of 500, we say, okay, 500 is my constant, times a growth rate of 25%. So notice right here, 1 plus our growth rate. So 1 plus 25%, or if we convert this into a decimal, this is 1 plus 0.25 to the power of t. That's it. Or x, or whatever your variable is. That's it. 500 times 1.25 to the x power. Ta-da! You're done. Super easy stuff, right? Nothing too crazy, nothing too complicated. Okay? Now you want complicated, I'll show you complicated. All right? Because the last problem on the test is one that I really like this problem, but it is a doozy. There's a lot of moving parts, a lot of things going on. But it's kind of stuff that you guys are going to see in the real world. And so I don't want to leave it off the test because it's hard. All right? So let's take a look at what we've got here. When a football player is injured, he does tutoring. At the moment, he has 15 students and charges $40 per hour. He has come to the conclusion that for every $10 he raises the price, he will lose 1 student. That's it. That's the situation. Very simple, very easy stuff, right? So, let's go ahead and see what this creates as an example. Okay? Our first question, is this situation best described as continuous or discrete? Remember that discrete, if I use this terminology, okay, discrete means that this happens incrementally. Okay? This happens incrementally or irregularly. It's not something that is constantly happening. Okay? Why is that important? Well, think about it this way. What if he only rose the price by $4? Would he lose 40% of a student? No, you can't really lose a fraction of a person, right? So what happens in that instance? Well, we don't know. We don't know what the breaking point was for that student who's going to lose. He's going to lose after he raises the price 10 years. We don't know if that breaking point is $1 or if it's $5 or what. So we can't say with any degree of certainty that he would lose that student or not. But we can say once he's raised it by $10, he'll definitely lose that student. Okay? Therefore, this function logically is best described as a discrete function. Okay? Now, what is the independent variable that the player has complete control over? Now, once again, this is a situation where we have to think about this, what's going on logically, and identify independent versus dependent variables. Okay? An independent variable is something that you have full control over, right? You can change it at your will, and other parts of the situation may change based upon you changing that. But you get to decide this one thing. Okay? And in this case, right, we've established that there is a relationship between the price and the number of students. And specifically, we've determined, okay, so that price is going to determine the number of students. Therefore, price is the independent variable. Okay? This player decides how much he's going to charge, and then he has a number of students based upon that. Now, next question. Write a function detailing the relationship between the price and how many students he has. Okay, so now we're getting into actually writing this function. Okay? And what I would like to point out is that when we're talking about writing this function, we need to identify first, what kind of function is it? Okay? Step 1, what kind of function are we dealing with? Are we dealing with an exponential function? Are we dealing with a continuous function? Are we dealing with a linear function? What are we dealing with here? And this boils down to the rate of change. Okay? The rate of change is going to determine what kind of function we're working with here. So, for every $10 he raises the price, he loses one student. So if he raises the price from $40 to $50 an hour, he loses one student. If he raises it from $50 to $60 an hour, he still loses one student. 60 to 70, he still loses one student. This is a consistent rate of change. And as this is a consistent rate of change, there is only one possible type of function that this could be, and it is a linear function. Okay? So we know we're working with a linear function. Now we have to identify, part 2, what form should we write this function in? Remember that linear functions have 3 main forms. Okay? There is the famous slope-intercept form, ye old y equals mx plus b. There is the second standard form, which says something x plus something y equals something. I don't know why they call it standard, because honestly, you don't draw as much information out of that as you do from other forms, but hey, whatever. You know, you can call it whatever you want to call it. Doesn't matter to me. Okay? The third form is point slope form. Point slope form. Okay? Now, of these, one is very clearly the best form for this situation, okay? Now, remember that the slope is the rate of change, okay? So if the slope is the rate of change, let's go ahead and identify this. So it's rise over run. So it is the change in your y over the change in your x. Well, how much does this y variable change? Well, remember that y is the dependent variable, okay? So since y is the dependent variable, that's students, okay? So he's going to lose one student. When is he going to lose one student? If he raises the price by $10. So if the price goes up by 10, students will go down by 1. That is your slope, -1/10. Now, with that, I'll go ahead and tell you right now that standard form is not going to help us here. Okay? But take a moment, think about it. What is going to be the best form? Slope-intercept or point-slope form? Do we know the y-intercept? We don't. We don't know how many students he's going to have if he charges nothing. But what we do know is how many students he has when he charges $40 an hour. We have that information. And therefore, we have a point and we have the slope. Therefore, point slope form is going to be the best form for us, which is y minus y1 equals m times x minus x1. Now you'll notice that I left some blanks here. I like to color coordinate things. So y minus y1 is going to be blue. The slope is going to be green. And x1 is going to be red. Okay? Now, you know what? I really shouldn't do that, actually, thinking about this. We're going to flip these. y1 is going to be red, and x1 is going to be blue. Why? Because I already identified those colors. Okay? So, let's go ahead and write the equation out. So, y minus equals x minus something else. Okay. What is our y1? What is our y coordinate? Well, it's the number of students at $40 an hour. So he has 15 students here, so y minus 15 equals the slope, -1/10. Right? We identified that right here. Equals x minus, and our x1 is how much he charges, -40. And just like that, we now have a point slope form function detailing what's going to happen here. Now, is this perfect? Well, in my opinion, it's perfect. It exactly serves our purpose. But as you'll see, as we detail other purposes, as we can kind of change what we're looking for, we're going to need a different form. Okay? Let's look at the next question. Write another function detailing the relationship between the price, the number of students, and the total revenue. Now, the way I've worked this out, your basic revenue works. And remember that revenue is calculated, the price times the number of sales, or in this case, the number of students, equals your revenue. Price times students equals revenue. Boom. Done. Okay? Now, I want to take this one step further, though, because we have another question. At what point will he maximize his revenue? Okay? And in order to figure that out, we're going to have to do something different. Because right now what we've got is we've got two lines, basically. We've got a line representing, oh, that's not what I wanted. That started drawing. That's not good. So marks up there. Okay, there we go. Okay. We have the price times the students equals revenue. And we have our nifty little function up there, okay? Now, what I'm going to do is we're actually going to convert our function from point slope form into slope intercept form. Why? Well, you'll see in a moment. Okay, so when we convert this, the first thing we need to do is distribute this -1/10. So this becomes y minus 15, that does not change, equals -1/10x. -1/10 times -40 comes out to +4. We then add 15 to both sides of the equation to get y by itself. That cancels out and leaves us with y equals negative 1 over 10x plus 19. Okay? Now, we're going to tweak this formula just a little bit because we're going to say, okay, students equals negative 1 over 10 of the price plus 19. Why did I do that? Because now I have what I need in order to calculate how he can maximize his revenue. Check this out. Oh, one of my friends just jumped on Path of Exile. All right. Price times students equals revenue. And students equals negative 1 over 10 times the price plus 19. Okay, so what I have done here is I have effectively set up these two functions side by side to show there is a relationship between them. And very specifically, I look at this S right here and this S right here. Because remember from IM1, we said, okay, if you see that a variable equals something else, you can plug that something else in place of that variable. And while in the past we've used this to say, okay, if S equals 5, right, then you can start to solve this problem. But now what we're going to do is we're going to say, okay, S is actually equal to this entire equation here. And what does that do? Well, behold, price times negative 1 over 10 the price plus 19 equals the revenue. We have now removed the middleman of calculating how many students he's going to have. So now we have changed our dependent variable from the price yields a number of students. We have replaced the students in this equation and said now I can take the price and I can directly calculate the total revenue based upon that price. Okay? And all we have left to do is distribute this. So P to that is negative 1 over 10P. And once again, I like decimals, so I'm going to say negative 0.1P plus 19P. And this is actually P squared here. And all of that equals the revenue. Okay? Now, take a look at that. Okay? So what we have effectively done here is we have removed students from the equation and we've created a quadratic equation that now represents this entire situation. So instead of having to calculate how many students he has and then using that number of students in order to calculate the revenue, now we have directly made ourselves able to calculate revenue based on how many students he has, or based on his total price that he's charging, okay? So what that does is it gives us this nifty little situation where we can now do this. We can slap this whole thing onto a graph. This is our graphing calculator in Desmos, and you'll notice that I have replaced the variables with X. The reason being Desmos doesn't know what to do with a variable like P or S, okay? It knows what to do with X though, okay? So X-axis down here represents, the X-axis down here actually represents how much he is charging, what the price is. So if he's charging $40 per hour, it's right here, okay? And I'm going to put a little line there to show X equals 40, okay? So this is how much revenue he is bringing in. He's got 15 students, and with those 15 students, he's bringing in a total of $600 a week, working 15 hours, okay? But what we can notice here is that the vertex of this is way over here, okay? Where if he charges $95, he's going to get about $902.5. Now notice, right, this treats it as a continuous, so that's why it's a line, okay? But if we were to just go to either side of this and say, okay, well, what if X equals 90? And what if x equals 100? Well, now we can click on these four dots here. And we can see that whether he charges 90 or whether he charges 100, he's now bringing in $900 every week instead of just 600. So by raising his price, right, he has brought in more revenue for himself. And we talked in class about this, but I do want to go over it. Let me go ahead and just make it to where you can see me here. We talked in class about this, but I do want to go over it again, how these are the types of calculations that if you're self-employed, you're going to be wanting to do on a fairly regular basis. Because you want to make sure that you know how much you're worth and you know how much you're bringing in. If you know that you can make an extra $300 per week and work less hours, why would you continue to serve 15 people at $40 when you could serve 10 at 90 or 9 at 100 and multiply your income time and a half? Right? It would be silly to continue to work at the previous rate when you can theoretically serve them better by working less hours. And then you could set up things like side hustles for yourself, right? You know, maybe you have another pet project you want to work on. Like, for instance, this YouTube channel is one of my pet projects, right? I was working 60 hours a week in the mortgage industry before I became a teacher, okay? And I'm making the same money as a teacher that I was in the mortgage industry, okay? Simply because I valued my time. And so now I'm only working 40 hours a week or so, give or take, you know, exams, finals week, all that, you end up working a little bit more. But now I'm working significantly less hours, and I have time to devote to things like setting up a YouTube channel, getting some branding established, and going forward and actually working on educating not just the students that I have in my classroom, but also students all around the United States and all around the world, possibly. I can expand my reach that way and develop additional income streams through additional projects, which is something I never could have done in the mortgage industry. But because I valued my time and saw an opportunity, we now have, you know, an extra little bit of thing where I can jump on and do a live stream to go over the final exam study guide with you guys, right? These are the kinds of calculations you're going to be wanting to do on a fairly regular basis if you are self-employed. And even if you're not self-employed, you may end up doing these calculations anyways, just as part of working for your employer. Okay? So while, yes, this problem is a doozy, and don't get me wrong, I understand that it's chunky. It's got a lot of steps to it. Okay? It is something that I have full confidence you'll be able to do because all the math in this is stuff you guys have done since I am one. You guys have been doing this. So I know that you can do the math. We've gone over the math too. This is one of the problems that you have the exact same problem on your final, but with different numbers. So long as you can follow the guidelines we've laid out here today with those different numbers, you're going to be just fine. I have full confidence. And I was talking with some other students during class, right? I'm not going to give you guys a problem on your final that I don't think you can solve. Everything on this final, I think, is fully within the realm of capability for you to solve. Okay? Now, that being said, that was all that I had planned for today. Does anybody in the chat have any other questions they would like to throw out before we go ahead and call the live stream for the day? I'll just hold for a couple minutes while you guys type. All right, well, if nobody has any other questions, which is what I'm seeing so far, then I'm going to go ahead and let you guys enjoy the rest of your Saturday. Thank you so much for tuning in. For those of you who were able to make it, for those of you who weren't able to make it, I hope that you enjoyed getting to watch some of this after the fact. I will have this up, and I'm just going to post it unedited straight to YouTube. Probably here in the next, I'd say 20 to 30 minutes or so, it'll be available. So whenever you get a chance to take a look at it, please do so. Please make sure to just, drop a like, drop a comment if you have any questions that I might be able to answer before we actually take the final. But other than that, you all have a wonderful, wonderful rest of your Saturday, and I will see you all in class for finals this week.